Hello lovelies, in this video we're going to be going through OCR-A, A-Level Chemistry, paper 2, the paper that we've written for 2024. So what we want you to do is to pause after the question comes up, have a go read this up, and then play the video and watch how we've worked through the answers, how we've structured it to clearly show the examiner everything that we need to get the marks. And then you can compare and see what you need to improve on.
Below is a molecule with the formula C9H10O. Identify which of these following groups are present in this molecule. So straight away here I can see that it's got this group here which I recognise is a carboxylic acid group. It's that classic C double bond O OH. I can also see I have an OH group attached to a benzene ring. Now I should be familiar with the fact that that's a phenol. It's tempting to call that an alcohol because it has that OH group, but because it's attached to the benzene, it's a phenol. So for that reason, out of these options, there is no ketone, there is no alcohol, but there is a carboxylic acid. And for that reason, option D is correct because only 3 is the correct functional group present in this molecule. So we'll put D in our answer box. Identify the number of peaks that would be seen in the carbon-13 NMR spectrum of the following molecule. Now the first thing here to consider is the symmetry in this molecule because that's going to have a real impact on it. We don't need to include both sides due to this symmetry, we can just look at one of the sides. So here's one carbon, here is another one, and another one, and another one. And actually in this benzene ring, all of these different carbons are in a different environment because if you were to draw like a little mirror line through it, you can see that it's not symmetrical and therefore every carbon there is actually different. So we did have symmetry, however, in this line here. And so all of the carbons on this side are the same environment as the carbons on the other side. So for that reason, we don't count them twice. They are the same environments. In this case though, you'll see that we found 9 different carbon environments. It's not the same as how many carbons there are, but the different carbon environments in this case is 9. Here we're asked to identify the conditions required to turn 2-ethyl nitrobenzene into 2-ethyl phenylamine. And let's start off here just by drawing these, because sometimes it can help us to visualise what they look like. Now we should know nitrobenzene looks like this, and 2-ethyl nitrobenzene has an ethyl group coming off of the second carbon. 2-ethyl phenylamine, well phenylamine looks like this. It's a benzene ring which has an NH2 group coming off of it. And in this case, we're going to have an ethyl group coming off of the second carbon again. Now if we place spot the difference, the only thing that's changed here is the NO2 group, that nitro group, has changed to an amine group. Doesn't matter about everything else has stayed the same. And so we should have it in our memory by this point that nitrobenzene going to phenylamine, you need tin and HCl. And that's how we answer this. We do just need to have that fact in our mind. However, we also need to recognise that they can add extra groups and things on, but that doesn't change it, okay? What we need to do is just spot what group changes and go to our memory and think, I know that when a nitrobenzene goes to phenylamine, I know I need tin and HCl. And what I find a lot of students struggle with is memorising these or realising the importance of remembering these reactions and their reagents and conditions that they need. So if that includes you and you didn't know this, then do stop for a minute and make some notes on how we go from nitrobenzene to phenylamine and how we need tin and HCl. And start to go through the rest of the course as well and start to write down all of these reactions we need to know and get memorising them as soon as possible. Identify the substance that does not produce an infrared spectrum. So to answer this, we need to remember what it is that infrared spectrums are used for. So infrared spectrums are generally used to determine the presence of functional groups of organic compounds. So here we need to think again, well, what is an organic compound? And very broadly speaking, we would expect organic compounds to be carbon containing and to have covalent bonds. So what we need to do here is to determine, well, are these substances organic compounds that could be sort of worked out via infrared spectroscopy, or are they actually not? And ethanoic acid is, as is 1-aminobutane, and the ethanoate part of sodium ethanoate. Potassium bromide, though, is not. It is just consisting of this ionically bonded potassium ion and bromide ion. For that reason, we would not get an infrared spectrum for potassium bromide, and so the answer to this one is D. Here we're asked to give the letter of the diagram that correctly represents a p orbital, okay? So they're just asking for one p orbital here. So we need to be familiar with the fact that p orbitals assume this dumbbell shape. We don't refer to them as a figure of 8 because that implies that they're two-dimensional, really. We need to get across the fact that they are three-dimensional in shape. And a dumbbell that we can use for fitness sort of sums that up somewhat. So we'll often see that way of referring to them. So if we look at all these options here, the only one that shows that dumbbell shape is going to be C. We might argue that the A looks a bit like two different sets of dumbbells, but here we're only being asked about a p orbital, just one of them. So C looks like a perfect fit. D, on the other hand, just in case they asked us, is that perfect spherical shape, and that would be the shape of an s orbital. So the answer for this question here is going to be C, okay? And it's that dumbbell shape that gives it away. Here we're asked to identify which row shows the correct oxidation numbers for the atoms in LiAlH4. So let's start just by writing out that formula nice and big so that we can annotate it. So the H4 in this is an example of a hydride. So a hydride is present when a hydrogen bonds to other metal atoms. And that's what we can see here in this case. So it's important that we know this fact, that when we have hydrogen bonded with metals, we have a hydride which has an oxidation number of -1, which is unusual because normally it's +1. So now we can take that into consideration. Of course, we know we have 4 of these -1s here. So -4 overall is coming from the H4. This molecule overall has a charge of 0. And therefore, we know that the Li and the aluminium have to make up +4. Now, lithium's in group 1, so +1 fits for that. And aluminium's in group 3, so +3 suits for that as well. So in this case, I can see that C is going to be the correct answer to this one. Identify which of the following would be the highest priority group according to the Kahn-Ingold-Prelog priority rules. So, before we look at this, let's remind ourselves of these rules. And this priority is when we're talking about CC double bonds and assigning priority to the groups so that we can name the correct E and Z isomers. So in terms of getting that highest priority group, for single atoms, a higher atomic number gives you the higher priority. So what you would want to do is to go through all the different groups and decide which one has the highest atomic number, and that's what you're going to say has that higher priority. Now, we don't have any single atoms here. Instead, we have groups. So let's have a look at what we do when we have groups. So what we want to do is we want to start by looking at the atom that's going to be directly bonded to the carbon of the CC double bond. Now, the one with the highest atomic number, again, you would say has the highest priority. If, however, they're all the same, then you start to move down the chain to neighbouring atoms and you carry out the same process. Well, let's put this into practice here, okay? So I'm just going to write out CH3 for A, B I'm going to write down as well, the same for C and D. And what I'm going to do, starting from the left-hand side, because that would show the carbon that would be bonded to the CC double bond, I'm going to apply these rules, and then I'm going to move through the molecule to work out what is the highest priority. And remember that it's the atom with the highest atomic number that will give the molecule a higher priority. So let's start with the first atom that will be attached to that carbon-carbon double bond. I can see that all of these groups actually just has a carbon. So we have to move on to the next group. So in A, that's an H, but in B, C, and D, it's carbon. So thinking of the atomic number of these numbers, we've got 1 for the hydrogen and 6 for the carbon. Now the hydrogen is now lower priority, so we cross that one out. That one is out of the running. And we move along now to the next atom. So for B it's O, for C it's H, and for D it's Cl. So let's remind ourselves of these atomic numbers. Hydrogen is 1, oxygen is 8, and chlorine is 17. So now we have a clear winner. We can see that D has the highest priority. And so D is our answer in this case. And so this is the method that you need to use if you ever had to use these Kahn-Ingold-Prelog rules. Identify the statement that is false regarding the formation of ethene from ethanol. So first things first, let us just write out the reaction and remind ourselves of it. So here we've got ethanol, although this could be any alcohol. And how do we turn an alcohol to an alkene, in this case ethene? So I'm going to draw it out just so we can visualise this a bit. So I've got my ethanol here, and then ethene obviously has this carbon-carbon double bond. So we should know that when we go from an alcohol to an alkene, we need an acid catalyst and heat. And these are the essential conditions needed for this reaction. So A is correct. Now for B, we're told that the bond angle of the product is less than the reactant. Let's have a look at some of the bond angles then present in ethanol. So we have 4 bonded electrons around the carbon. That gives us an angle of 109.5. Around the oxygen, we've got 2 bonded pairs and 2 lone pairs. That gives us an angle of 104.5. However, when we look at the ethene, we have 3 regions of bonded pairs of electrons. And of course, no lone pairs. Now we should recognise that that corresponds to a bond angle of 120, which is certainly a bigger bond angle than the reactant. So this statement that the bond angle of the product is less than the reactant is incorrect. So in theory here, as this is a multiple choice, we could just write that down and run. But let's just chat through the rest here as well. So the next point talks about sigma bonds being present in the reactant. And that's correct. Ethanol does only have sigma bonds, whereas the ethene, because of that CC double bond, it does have overlapping p orbitals, and therefore it has a pi bond. But that's the product, not the reactant. And finally here, this is indeed an example of an elimination reaction. A water molecule is removed from the ethanol to form ethene. And so the false statement here is indeed B. 6.8 grams of this hydrated salt was heated until a constant mass of 4.1 grams was reached. And we're asked to calculate the value of X in the hydrated salt, assuming that no decomposition took place. So in order to work this out, let's think about this. We know the mass of the hydrated salt, and we also know the mass of the anhydrous salt, which is the mass after it's been heated and the mass has stopped changing. So if we do the mass of the hydrated salt and take away the mass of the anhydrous salt, we will be left with a mass of water. So 6.8 minus 4.1 gives us 2.7, and that is our mass of water that we have in this hydrated salt. So to work out the value of X in the hydrated salt, what we need to do now is work out how many moles we have of the anhydrous salt, of the CH3COONA, and also how many moles of water we have. So I like to use a little table to help me with questions like this. So I'm going to write down the masses, the MRs, and then I will get the moles. So the mass of our anhydrous salt is 4.1 grams. the mass of water is 2.7 grams. For the MRs, we should already be familiar with the fact water is 18, but of course we can work it out. But now we need the MR of sodium ethanoate. So here we've got 12 plus 3 times 1 for the hydrogens, plus 12 for another carbon, plus 2 times 16 for the 2 oxygens, and then plus 23 for the sodium. Now in total there, that gives us an MR of 82. So we can work out the moles now. Moles is just mass over the MR. So for the salt here, we've got 4.1 over 82, which gives us 0.05. And then for the waters, the moles will just be 2.7 divided by 18, which gives me 0.15. Now that is our ratio of the moles. We want the simplest whole number ratio though. So we can do that by dividing by the smallest number, in this case 0.05. That gives me 1 to 3 for the water. And so the number of waters, X, is going to be equal to 3. And so that is our answer to this question. A chemist added aqueous silver nitrate to solutions of 1 bromobutane and 1 chlorobutane that had been dissolved in ethanol. The time taken for precipitate to form was 63 seconds and 422 seconds respectively. Here we're asked to predict the time taken for a precipitate to form when 1-iodobutane was tested. Assume the volumes and concentrations used are equal for all 3 experiments. So, we know it took 63 seconds for the precipitate to form when we had 1 bromobutane, and we know it took 422 seconds when we used 1 chlorobutane. So when it comes to predicting the time taken for a precipitate to form when we use 1-iodobutane, we need to remind ourselves of group 7. We can see here that when we used chlorine, it took 422 seconds to form a precipitate. Bromine was 63 seconds. I think even if we didn't remember any additional information here, we can see a trend developing. However, we should be familiar with the fact that the rate of hydrolysis increases as we go down the group, which means that this reaction will be taking faster. That means that we expect the iodine to take less time to form this precipitate. Now, the only option here that fits for that is going to be A, which states 25 seconds. And so that is our answer to this one. Here we're asked to identify the number of chiral centres, if any, in the substance of 2,3,4,4-tetramethylhexane. So the first thing that I would do here is draw out that molecule. So I can see it's hexane, so I know that the longest carbon chain is going to be 6 carbons in a row. I know that there's 4 methyls because that's what tetramethyl means, and they're on the 2nd, the 3rd, and I have 2 on the 4th carbon. So I've got here what this molecule looks like, my 2,3,4,4-tetramethylhexane. So the next thing we need to do here is to remind ourselves of what does it mean, chiral centres. We should know that chiral centres have 4 different groups attached to them. So not just atoms, but groups attached to them. So we need to go through each of the carbons here one by one and see if they have 4 different groups. This first carbon has 3 hydrogens, doesn't have 4 different groups. This next carbon here, I can see it's got a methyl group to the left of it, and below it has another methyl group. So it doesn't have 4 different groups attached, so that is not a chiral carbon. Now on to the next one. Here I can see this carbon here. It's got an H above, it's got all of this to the left and to the right, which are different, and it's got a CH3 below, which is also different. That means that that is a chiral centre there. On to the next one. I can see it has 2 methyl groups, one above and one below. That means that that does not have a chiral carbon. The next one, I can see that this carbon here has a hydrogen above and below. So it doesn't have 4 different groups, so it's not a chiral centre. This one on the end here, same idea, it's got 3 hydrogens attached, and therefore it can't possibly have 4 different groups attached, so that carbon also isn't. Let's not forget some of these branches there were carbons too though, wasn't there? This has 3 hydrogens attached, so not 4 different groups. Same goes for this one underneath, and actually all of these other ones too. Because they have 3 hydrogens attached, they don't have 4 different groups. So therefore we only found 1 there, and so the answer to this is B, okay? So the answer we want to put in our box is B. Identify which of the following substances could have produced the infrared spectrum below. So here I can see 2 significant peaks that I want to talk about. So I can see that this region here that I've highlighted is a strong peak within the region of 1630 and 1820 centimetres to the -1. Now I know from looking at the data sheet that this particular peak tells us that we have C double bond O present. So now let's look at this other broad peak that we have here, which exists within the range of about 2500 and 3300 centimetres -1. So I know, again, simply by looking at the infrared spectroscopy part of our data sheet, that this broad peak corresponds to an OH group, and specifically an OH group belonging to a carboxylic acid. So here I've got this C double bond O and an OH belonging to a carboxylic acid. If I look at the options here, I can see A is just an alcohol, B is another alcohol, C is a ketone, so it has that carbonyl group. However, D is hexanoic acid, which is a carboxylic acid. Now D is the only one here that has both that carbonyl group and the OH belonging to a carboxylic acid. Although the others might show one of those peaks, they don't show both. And so as a result, the answer to this one is D. Identify which statement about the mass spectrum of 2-chloropropane is false. So let's start this off just by simply drawing out the structure of 2-chloropropane, just so we've got it in front of us to consult. So we can see here that we've got carbons, we've got hydrogens, and we've got chlorines. And it's worthwhile remembering that we get isotopes of these different types of atoms, particularly the chlorine. Think about just the mass number of chlorine on the periodic table. It's 35.5, isn't it? And the fact it has that decimal tells us that we have a certain amount of different isotopes present. The mass of chlorine isn't actually 35.5, that's the relative mass. And so it's actually the average mass of all of the isotopes. If we were simply trying to work out what the MR is of 2-chloropropane, everything would end up adding up to eventually give us 78.5. However, that is not a peak that we're going to get on the mass spectrum, because there's no atoms with a mass of 35.5. Instead, with chlorine, we actually get isotopes with masses of 35 and 37. For that reason, we know we're not going to get a peak at 78.5. So even without thinking about the others, we know that that isn't a possibility because that won't represent the mass of any of these molecules. And so the false statement here is B. If we have a look at these other statements though, and we just have a think about, well, why are they true? The molecular ion peak of C3H7Cl, if we use the chlorine 37 isotope, would end up having an MR equal to 80. And so we would expect to see a peak at MZ 80. So that's why D is actually correct. Now we can use that fact to identify why A is correct as well. An MZ peak at 43 could be there because that MR of 80, that molecular ion peak, has had the chlorine removed. That leaves us with a CH3 CH plus ion, and that would be the fragment causing this peak at MZ43. Now, this statement at C that a peak is observed at MZ63, which is 3 times bigger than the peak at 65, that's going to represent the CH3 CHCl plus ion. And the reason why we've got a peak at 63, which is 3 times bigger than that at 65, is due to the fact that the isotope of chlorine 35 is 3 times more abundant than that of the chlorine 37 atom. And so therefore we're going to have 3 times as many of this 63 mass peak than we do of 65. So that would also be correct as well. So although we could see that B was the correct answer without looking at the rest, and that is how we should treat the multiple choice in the exam, it's always worthwhile just going and having a look together in this little safe space just to explain why the others are in fact true. Here we're asked to identify which of these reactions would form pentane nitrile. So, looking at these first two, which involve a carbonyl group and HCN, we should know that that reaction is going to form a hydroxynitrile. And that's not what we're looking for here, we're just looking for a nitrile. However, we should know that if we have a haloalkane and we react it with NaCN, we do in fact form a nitrile. And as a bonus, I'm going to show you the mechanism here. So the CN- with a lone pair from the NaCN is going to react with the halogenoalkane. I've got this dipole of delta plus on the carbon and delta minus on the chlorine. And you can see here that we have this nucleophilic substitution reaction taking place, whereby the CN nucleophile is going to replace the chlorine. And so I can see that that does indeed form pentane nitrile. I can see I've got this 5-carbon chain with a nitrile group attached, and so C is our answer to this one. Here we need to identify which of the following could form a polymer with only one monomer. Now, they've given us all these structures, but I'm going to say let's draw each of these out just so that we're really clear of what functional groups we have, and we can have a good think about which one might be able to have a polymer with just one monomer. So A here is an acyl chloride. Okay, drawing it out, it becomes really, really clear. B, on the other hand, is going to have an alcohol group and also a haloalkane group. So it's just got a C to a Cl within it as well. All of the sticks that don't have hydrogens attached, please know that they should have hydrogens attached, but I'm just not drawing everything because it's not necessary for the sake of this question. It's just as a visual aid. Now C, on the other hand, I can see that this has an OH group. It is an alcohol, and it also has a CC double bond, and that there is very important. Now finally for D, I can see that I have 2 carboxylic acid groups. So I'm going to draw that on here with a carboxylic acid on each side of this molecule. So now let's have a reminder of what type of polymers exist. So we have addition polymers and we also have condensation polymers. Now condensation polymers rely on a chemical reaction taking place, and they can happen with just one monomer. But we would expect to have, say, an alcohol and a carboxylic acid, or an amine and a carboxylic acid, or something like that. We don't have that here. However, we do have an alkene group. And alkenes, we should know, can form addition polymers. And addition polymers do just have one monomer. They just open up the arms of that double bond and then repeat, repeat, repeat. And so in this particular case, the answer to this is C. C is the only molecule here that could form a polymer consisting of one monomer. Butanol is an aliphatic alcohol which is used as a fuel and a solvent. The image below shows a molecule of butanol with some bond angles labelled. Here we're asked to suggest values for bond angles X and Y. And so we need to have a look at these here and think how many bonded pairs and lone pairs are around these central atoms. I can see that carbon is bonded to 4 hydrogens, and therefore that carbon will have 4 bonded pairs of electrons surrounding it and no lone pairs. You need to know that when we have 4 bonded pairs and no lone pairs corresponds to a bond angle of 109.5 and a shape of tetrahedral. So that's how I know this one here. Now looking at this oxygen, I can see I have 2 bonded pairs and I have 2 lone pairs of electrons. Now I also expect you to know that when we have 2 bonded pairs and 2 lone pairs around one atom, we have a bond angle of 104.5 and a shape of non-linear or bent. So if you didn't already know that, then make sure you go away and make some notes on that now, okay? Alright, so excluding butan-1-ol, give the number of structural isomers that are alcohols that have the molecular formula C4H10O. So we know we can't have butan-1-ol, but let's have a look at having a straight chain, so still but let's put the alcohol on the second carbon instead. That would be butan-2-ol, and that is certainly another isomer. If we kept moving that OH along though, then we just get the same butan-2-ol again, and then butan-1-ol again. So we're finished there with the straight chain. Now let's shorten it so that it is just 3 in a chain, but we have a branch of a methyl group. We could have something that looks like this if we did that. We could have 2-methyl propan-2-ol, where the methyl group and the OH group are both coming off of our second carbon of a 3-chain alcohol. And the last thing we could do is along a similar idea, but let's again have a go at moving that OH group. How about we still have that branching, however we put an OH group on the end. And that would end up having a name of 2-methyl, because we still have a methyl group on the second carbon, propan-1-ol, because we have our alcohol group on the first carbon. So there we have it. In total there we have 1, 2, 3 different isomers. There's no other ways we could just shorten that chain more, because it would actually end up having the exact same structure as one of the other ones we've already named here. So we've got all of our options. We have 3 different structural isomers, excluding butan-1-ol. Compare the solubility of butan-1-ol to that of ethanol. You should include a diagram to show why ethanol is soluble. Okay, so when we do compare butan-1-ol to ethanol, you can see that they're both straight chain alcohols, so there's nothing to do with branching that's going to cause any differences. However, ethanol is a shorter chain, and that's what's important here. So when we compare their solubilities, we should know that ethanol is more soluble than butan-1-ol. Now the reason for this is that ethanol is going to have a shorter non-polar part to it. We know that the OH group will be polar, but the non-polar region of it is much shorter, and that is that carbon-carbon chain. Of course, ethanol only has 2 carbons in its chain, whereas butanol would have 4 carbons in its chain. And therefore the non-polar region would have a much bigger impact in butan-1-ol, and that would have a knock-on effect on its solubility. So here, when we compare the solubilities of butan-1-ol and ethanol, we need to know ethanol is more soluble, and that's due to the fact that ethanol has a shorter non-polar carbon-carbon chain length. Next up though, we have to include a diagram to show why ethanol is soluble. So here we want to draw it out showing all of its bonds, and we want to make sure that we show the dipole on the oxygen to hydrogen. So for that reason, looking at this, it's delta negative on the oxygen, and we have a couple of lone pairs there, whereas the hydrogen is delta positive. Next up, let's draw water next to it, because we're looking at solubility, and so what's important there is how it bonds to the water. Water has an oxygen in it as well, that has 2 lone pairs of electrons, and it has a delta negative oxygen and a delta positive hydrogen. As you can see here, the delta positive hydrogen is going to be attracted to the lone pair on the oxygen of the other molecule. So here I've done it with the delta positive hydrogen of the ethanol, and I've shown how it gets attracted to the lone pair of the oxygen on the water. However, you could have done this the other way around as well, and it still would have been correct. So you could have instead shown the delta positive on the water being attracted to the lone pair on the oxygen of the alcohol. It would work exactly the same, you're getting the same idea across. But to get the full marks for the diagram part of this question, what we need to do is we need to include our dipoles, our delta positive hydrogens and our delta negative oxygens on both the ethanol and our water. And we also need to make sure that we show a hydrogen bond forming, and that is going to be with the lone pair of an oxygen on one of the molecules with a hydrogen on the other. And make sure as well that you label our bond as a hydrogen bond. And there we have all of the things that you need to say to get your 4 marks in this question. Butan-1-ol can be synthesised from a carbonyl. A test for carbonyl groups is to use 2,4-dinitrophenylhydrazine, 2,4-DNP. Describe what's observed when 2,4-DNP is added to a substance containing a carbonyl group. So we need to know that the observation when 2,4-DNP is added to a carbonyl group is an orange precipitate forms. So that's our answer for this. And if you didn't know that that was the positive test, make sure you pause the video now and just make a note of it. Explain why the carbonyl used to make butan-1-ol must be butanal and not butanone. So what we need to recognise in this question is that butan-1-ol is a primary alcohol, isn't it? So if we were using butanone, which is a ketone, what we would make is actually a secondary alcohol. Only butanal could react to therefore make a primary alcohol. So the whole basis of this question is understanding that difference between primary alcohols and secondary alcohols and how they can be made from either ketones or aldehydes. So yes, in this question here, the reason why we need to use butanal and not butan-1-ol is because butan-1-ol is a primary alcohol, whereas butanone, which is a ketone, will form a secondary alcohol. In the mechanism, the C-double bond O group in butanal breaks and forms a negatively charged intermediate. Identify the name of the bond fission that has occurred to form the intermediate. So the answer to this is heterolytic bond fission. And I think it's really important to mention here that at A level, the only time we get homolytic bond fission is when we're using free radical substitution. Whenever we're just doing normal bond breaking and we're getting positives and negatives along the way, we have heterolytic bond fission. So as a general guide, unless the question is very obviously about radicals and they ask you this question, the answer will probably be heterolytic fission. If it is talking about radicals, then the answer is homolytic fission. So on to the next bit. Construct a balanced equation for the reduction of butanal to butan-1-ol. You should use H in square brackets to represent the reducing agent. So we should know that whenever we do one of these reductions, be it from an aldehyde to an alcohol or a ketone to an alcohol, we need 2 of these reducing agents. So if you look through your molecule and count up how many aldehydes or ketone groups, each one of those will require 2 of these reducing agents. So here you can see I've got the formula for butanal, I've got C4H8O, and then I've added on 2 reducing agents, and that's going to make our alcohol. So just to show you that, so we had butanal. Just in case you didn't know what the molecular formula of that might be, you can draw it out, count up how many atoms of each type, and then it makes the alcohol. So finally here we're asked to identify the reducing agent used in this reaction. So the answer to this is aqueous NaBH4, or you could write that in words, that is sodium borohydride. And that is a really, really easy mark that we absolutely have to know. Okay, you have to know that that is the reducing agent used in these reactions. NaBH4, it should just come to you super quickly. Okay, so lots of really key facts in this question that we need to know. So if there's anything you didn't know, just make some notes on it. A chemist was given 2 substances, L and M, as shown in the image below. Here we're asked to give the IUPAC name of substances L and M. So L is a very common substance that we see a lot in A-level chemistry, and we should recognise that compound L is phenol. Compound M, on the other hand, isn't a phenol. It has this benzene ring that we have here, and it's got a branch coming off of it which involves an alcohol group, okay? Now, because this benzene group is secondary to the alcohol, when we name it, we're not going to use it as benzene in the name. We're going to name it as a phenyl group. And that's really important. So if we start numbering this then, we can see that the phenyl group is on the first carbon as is that alcohol group. So we have 1-phenyl propan-1-ol, because that longest carbon chain, if we're not including that phenyl group, is 3 carbons long. So 1-phenyl propan-1-ol. And it's important that you know that when you have a benzene in it, it's not always necessarily called benzene, but we might need to refer to it as this phenyl group instead. The chemist added bromine water to both compound L and M. Describe what the chemist observed. Give equations for any feasible reaction and draw the products formed. So let's start off by rewriting out what L and M are so that we can actually have a think about them. And whenever we're being asked about what chemical reactions may or may not happen, it comes down to what functional groups are present. So if we start with looking at L, I can see that that is a phenol group, as we talked about in the last part of the question. Whereas on M, I can see I have an alcohol group and a benzene group. So we need to ask ourselves, have I learned that bromine water reacts with any of these different functional groups? And we should recognise that bromine water will react with phenol. We should know that when bromine reacts with phenol, we end up making 2,4,6-tribromophenol. And what we'll observe in that case is because the phenol reacts with the bromine, effectively removing it from the bromine water will decolorize, and we will also form a white precipitate. And that white precipitate is the 2,4,6-tribromophenol that is formed. So we have described what the chemist observed there. We also need to give equations for any feasible reaction and draw the products formed. So before I do that, I'm just going to draw out the product just so that we know what it looks like. So 2,4,6-tribromophenol looks like this. And I can see, as the tri part of the name implies, there are 3 bromines attached to it. Now what that means is when we write out our balanced equation, we're going to have our phenol and we're going to have to add 3 Br2s. As a result, we make this chemical, and we could draw this if we needed to in our equation. I'm going to write it as C6H3Br3O, and then I get 3 HBRs made at the same time. So that there is my balanced equation, and I have drawn the product formed. And I'm just going to add in the name here, 2,4,6-tribromophenol. So that's all the reactions that our phenol will have with bromine water. So if we now have a little look at this molecule, M, we know it's got alcohol and benzene in it. Now we haven't learnt anything at all about how bromine can react with either of those. It can't. And so we're going to observe no reaction here. The bromine water will remain orange and it will not decolorize. And so we don't need to do anything else there. We don't need to give any equations or draw any products formed because nothing happens now. The acidity of compounds L, M and propanoic acid were compared. For the following bases, identify which of the compounds underwent a neutralization reaction. Put a tick in the box if a reaction was observed. So again, let's just remind ourselves of what L and what M are. L was the phenol, and M was our benzene that had an alcohol attached to that. So let us get started now with compound L. And let's ask ourselves, will that react with sodium hydroxide? So we should know that phenol can act as a weak acid. It's not quite the same as a carboxylic acid. It doesn't react with everything, but it can react with bases in the same way. So for that reason, yes, sodium hydroxide is going to react with compound L. However, and this is the really important thing to know about phenol, it does not react with carbonates. And that's the difference between phenols and propanoic acids. Carboxylic acids will react with hydroxides and carbonates to form a neutralization reaction, but phenols only react with hydroxides. Now looking at compound M, we have an alcohol and a benzene, don't we? Neither of those react with hydroxides or carbonates, and therefore we're going to put some crosses in those boxes. And there we have it, that's that one finished. Polymers are an important group of substances due to their wide range of uses. Unfortunately, due to their high stability, they take many years to decompose. Research is ongoing to synthesize biodegradable polymers. The polymer PHB is a plastic that has many uses, including disposable cutlery and cups, and in medical applications such as patches and stitches, due to its being biodegradable. The monomer that forms PHB is shown below, and it's called 3-hydroxybutanoic acid. Here we're asked to name the reaction that forms PHB and identify the other product that is made. Well, of course, the first thing to realise here is that PHB is a polymer. And we only really learn about two different types of polymers. We learn about condensation polymers and addition polymers. In this case, this molecule that we have here has a carboxylic acid group and an alcohol group. We should know that that is a type of polymer that's called a condensation polymer. And the reaction that takes place to make that type of polymer is a condensation reaction. And during this condensation reaction, we end up making water molecules too. So that's what we need to say to get our marks here. Now we're asked to draw the polymer PHB that forms from 3-hydroxybutanoic acid. And we're told that we should draw 3 repeat units. So in order to do this, the first thing that I would personally do is I would just draw this out in a way that I feel the most comfortable with. I quite like drawing it in this way here, but of course, if you like keeping it in skeletal formula, by all means do. So what I'm making a real special effort to do is to make sure that that OH group is on the opposite end to the carboxylic acid group. And the reason why I've done that is it's going to make it much easier to draw them next to each other and therefore show the formation of that bond. So the reason why I'm putting these sat next to each other, these two different monomers, is if I now show the removal of a water molecule, I can also show the formation of the ester bond between them. And so what happens here is that oxygen of the C double bond O bonds with the carbon of the other molecule. Now, this also has an effect on either side because this is a polymer. We're not just making like one bond here, we're making lots of them. So we're going to essentially remove a water from the opposite ends as well, like you can see here. Now what we've got here is a repeat unit with 2 units. What we need to do here is add an additional one. But now that we've seen this, it should be clear how we do 3 repeat units. So I'm starting here with my purple region. Now I'm going to do a blue one, okay, to show a different repeat unit. But notice the building block of it, it's exactly the same. It's like I've just cut and pasted the purple molecule and just repeated it. And that is the purpose of a repeat unit. It should always go that way. Now let's mix it up with another colour to show our 3rd repeat unit. Again though, that unit that I'm repeating is just going to look identical. So I'm just going to do that carbon with a hydrogen and a CH3 attached to a carbon with 2 hydrogens, and then attached to my carbon with my double bond O and my O bond. And notice there, really importantly, at the ends, I have left them open. I haven't terminated them, I've got these open ends. And that shows that it's a polymer. Okay, so finally here, we're asked to identify what type of polymer PHB is. So, because it has this ester linkage, it is a polyester. However, you could also get the mark in this case if you stated a condensation polymer as well, because it certainly is a condensation polymer. However, all the better if you can be a bit more specific and state that what we have here is actually a polyester. 1 kilogram of PHB was synthesized. Calculate how many repeat units are in 1 kilogram of PHB. Give your answer in standard form to 1 decimal place. So to be able to work this out, as we're talking about repeat units, is we need to remind ourselves of what the repeat unit was. So here I'm just going to copy it down again quickly. So once we do this, we need to get the MR, okay? So I can see that this particular repeat unit has 4 different carbons on it. I can see that there are 6 different hydrogens on it, and also 2 different oxygens on it. So when I go to calculate that MR then, I'm going to do 4 times 12, and then plus 6 times 1, and then finally 2 times 16 for those oxygens. And I end up getting there an MR of the repeat unit equal to 86. And now we've got that MR of the repeat unit, we can work out how many moles of repeat units we have. So I know then that moles equals mass over MR. The mass of PhB is 1 kilogram, which is 1,000 grams. So we've got moles equals 1,000 over 86. Now that gives me 11.6279 moles of our repeat unit. However, we're not asked for how many moles of repeat unit there are. We're just asked for how many repeat units. And so we need to use Avogadro's number. If we multiply the moles by Avogadro's number, we get the actual number of repeat units. So that's equal to 11.6279 times by 6.02 times 10 to the 23. And that gives me, to 1 decimal place, 7.0 times 10 to the 24. And so that there is our answer. That is the number of repeat units we have. And it's always worthwhile just double checking at the end. We have given our answer in standard form, and we have given it to 1 decimal place. So there you have it. That is our answer. So now the next part of this question asks us to suggest a reason why PHB is considered biodegradable. And this is quite a common question, so do make sure you know this answer. The reason it could be considered biodegradable is because due to its ester linkage, it can be hydrolyzed. And so that is a good standard answer that we need to know. 3-hydroxybutanoic acid can also form other substances. Describe how 3-hydroxybutanoyl chloride can be prepared from 3-hydroxybutanoic acid. And we're asked to explain any safety precautions that need to be taken due to the products that form. So what we need to recognise here is although these have really fancy names, essentially we're going from a carboxylic acid, this 3-hydroxybutanoic acid, to an acyl chloride. The 3-hydroxy bit doesn't add anything to it because that bit hasn't changed. We're just looking at the bit of the name that's changed. And we should know that when we do want to turn a carboxylic acid to an acyl chloride, we need to add SOCl2. Now, when it comes to the safety precautions here, we need to bear in mind that gaseous hydrochloric acid is formed. And because of this harmful gas being produced, we must ensure that we use a fume hood. So those are going to be our safety precautions and our explanation as to why we have to take those precautions. And that's how we get our 3 marks. So the next part tells us that the acid anhydride derivative of 3-hydroxybutanoic acid is shown below. The acid anhydride derivative is more reactive than 3-hydroxybutanoic acid. Here we're asked to draw the products that are made when this acid anhydride is reacted with ethanol at room temperature. So in order to answer this, we need to know this reaction. We need to know that when we react an acid anhydride with an alcohol, such as ethanol in this case, we end up making 2 products. We make an ester and we make a carboxylic acid. That fact is vital to being able to work out this question. So if we go back to the molecule that they've drawn out here, and let's imagine that we break the bond just here. So we can imagine now that this is going to form 2 parts. And those 2 parts are going to have had some reaction with the ethanol, okay? That 2-carbon alcohol. Now what I'm drawing here is one of the possible products. Notice that we can imagine that if the C2H5O part of the ethanol bonded to this side of our molecule. And then on the other side, imagine I draw exactly sort of what I see here, all of this, but I attach to that oxygen there the hydrogen from that ethanol. Then I have completely shown the two products, my ester and my carboxylic acid, that are going to form when we break this apart using ethanol particularly. And so it's really important that we know this reaction, that an acid anhydride reacts with an alcohol to make an ester and a carboxylic acid, and that we know how those new bonds form, as you can see here. Benzene is a naturally occurring aromatic compound whose existence was discovered in 1825. The structure of benzene was difficult to establish, and for a long time the Kecule model was widely accepted by the scientific community. Later evidence was produced to prove the delocalized structure. To start us off here, we're asked to state the empirical formula of benzene. So to be able to do this, let's first remember what the molecular formula of benzene is. So the molecular formula of benzene is C6H6. So remember, the empirical formula is the simplest whole number ratio. That's just going to be a 1-to-1 ratio. So the empirical formula is just CH. So now we're asked to explain the evidence that proves the delocalized model is the correct model for the structure of benzene. And there's 3 facts here that you need to know well. The first one is that in the Kecule structure, we would expect there to be different bond lengths, some of the bond lengths belonging to a CC double bond and some a CC single bond. However, in reality, when they did some experiments on this, they found that all of the CC bond lengths were the same. Now, this disproved the Kecule model and suggested a different model, such as the delocalized model. So now on to the second fact. When we react benzene with bromine water, we observe no reaction. Now, if in fact it was the Kecule model, the presence of those CC double bonds means that it should decolorize bromine water. And so the fact it doesn't tells us that it can't have this Kecule model. It must be something different, such as the delocalized model. Now finally, the final fact is about the enthalpy of hydrogenation. So every CC double bond has a certain enthalpy of hydrogenation associated with it. If we had the Kecule model, then we would expect it to be 3 times that. However, it's not. The enthalpy of hydrogenation is less than we would expect it to be if it did have 3 of these C-double-C bonds. And that again tells us that we can't have this Kecule model. We must have something different, such as the delocalized model. So, as this is just a 3-mark question, we don't need to go into too much detail. Just 3 good, short, snappy facts is what we need. So the first thing to get the first mark is just that the carbon-carbon bond lengths are all the same. The second thing we can state is that benzene does not decolorize bromine water. And the final thing we can say is that the enthalpy of hydrogenation is less than it would be if we had 3 carbon-carbon double bonds. Benzene is a useful starting point to build more complex molecules. An example of such a multi-step reaction pathway is the formation of methyl benzoate, as shown below. Here we're asked to name the catalyst required for the formation of methylbenzene with benzene. Now this process requires a halogen carrier, and that is what our catalyst is in this case. So we need to know that the catalyst here is AlCl3, and that is a fact they expect us to know. Now we're asked to give the name of the substance that was reacted with benzoic acid to form methyl benzoate. And see here, we had this OH group on the benzoic acid, and that has changed due to this reaction. Instead of having an OH, we now have an OCH3. Now let's draw out this benzoic acid and let's imagine what we would need to react with that to get this OCH3. Now how about if we had a condensation reaction take place? What about if we had a CH3 and an OH? What would happen then is a water could be removed via a condensation reaction and forming this bond between them. What we have here is actually an ester bond. And so what we need here is going to be methanol. And that is the substance that needs to be reacted with benzoic acid to form methyl benzoate. Methyl benzoate can undergo nitration to make methyl-3 nitrobenzoate, which is used to train dogs to detect illegal drugs. Here we need to name the mechanism for the nitration of methyl benzoate to methyl-3 nitrobenzoate. And the thing to notice here is that the only thing that's happened is a nitration. It's irrelevant that it's a methyl benzoate or not. We should know that if we had any benzene and we nitrate the benzene using the NO2 plus electrophile, we have an electrophilic substitution reaction happening. So just strip away all of the fancy stuff. Just go back to what you've learnt and see how you can apply it to the question. And that's really what organic chemistry is all about at A-level. So now we're asked to draw the mechanism for the nitration of methyl benzoate to methyl-3 nitrobenzoate. And we need to show how sulfuric acid acts as a catalyst in this reaction. I love these questions because you have 5 guaranteed marks if you have learnt this process. It is the same every single time. So first up, we write down an equation that will show the formation of our electrophile. So here we have H2SO4 plus HNO3, and it makes HSO4 minus plus NO2 plus H2O. And here we have shown that we've formed our electrophile of NO2 plus. Now we're going to get to the mechanism. We're used to it just being benzene reacting with the NO2 plus, but I want you to know it doesn't matter. We're just going to draw it looking a little bit different. There is a benzene here, so it will still react in the same way. The one thing we need to be careful of though is which carbon we're going to attach that NO2 to. I can see that it's not the top carbon in this case. It is actually the third carbon. So that means we need to show our arrow moving from our ring from that area. We can't just do it from the top like we've learned in the textbooks. We always need to keep an eye on where we're going to attach the group and show the arrow coming from there. So that process of that curly arrow has broken that ring of electrons. So now we've got this horseshoe facing that third carbon again, and we have made a bond with the NO2. We've got that bond with a hydrogen that was there all along, but we never bothered to draw it before because we just didn't need it. But now we do, because we've got too many bonds here now. And what we're going to do is we're going to show the breaking of this bond with the hydrogen by donating its electrons back into the ring. That now has reinstated our ring. We would have formed an H plus ion as a result of this, and we have the NO2 attached. And see how the whole way along, this group on the top just happened to be there. We didn't do anything to change it. It just stayed there. It didn't bother us. We didn't need to think about it. We just cracked on with it. And that is what you need to do in the exam. So now finally, let's show that sulfuric acid acts as a catalyst. So all we need to do to show this, and again this is the same every single time, is to take the HSO4 minus that we formed in our first step, add it to the H plus that we formed in this mechanism, and show that it makes H2SO4. And it's that fact that we have reformed the sulfuric acid after initially using it that shows that it acts as a catalyst. See, wasn't that just so lovely and dreamy and such easy marks? So make sure that you don't miss out, and if you don't know this mechanism, just make sure you get learning it now. Here we're asked to describe a method for the formation of pure dry sample of methyl-3 nitrobenzoate from methyl benzoate using sulfuric acid as a catalyst. So that's asking for the method as to what we've really just looked at in terms of that mechanism. We're asked to include in your response how the purity could be assessed. So we need to know the actual experimental procedure behind this nitration of benzene, or in this case, methyl benzoate. So let's have a think of these steps. Let's start off with step 1, which is all about the preparation of it. So we're going to start off here by mixing methyl benzoate and concentrated sulfuric acid in a flask and then placing it in an ice bath. That is our very first step here. Next up, we're going to take some concentrated sulfuric acid and concentrated nitric acid, and we're going to mix them together in a different flask and again place them in an ice bath. So now we're going to mix these together drop by drop. After that, we're going to give them a stir and then leave them at room temperature. Our next step of this method is we're going to add ice and we're going to stir it. And we should observe a precipitate forming. Once this precipitate forms, we're going to do filtration under reduced pressure. This should lead to the formation of some crystals, which we will then wash. So now we have done that, we need to think about the recrystallization process, which is our second step of making this. Our first step of this recrystallization process is we're going to warm up some ethanol. So once we've done that, we're going to dissolve the crystals that we formed in a minimum amount of warm ethanol. So once we've finished this, we're now going to filter, and then once we've done that, we will leave this to cool. Now we go back to filtering under reduced pressure. And then after that, we're going to wash with distilled water and leave our crystals to dry. Now these steps would have formed our pure dry sample of methyl-3 nitrobenzoate. However, to get the full marks in this question, we need to include in our response how the purity could be assessed. So a method that you could use to do this is we could measure the melting point and compare it to a known standard. So we could look it up in a textbook and say, well, what is the melting point of methyl-3 nitrobenzoate? And if the melting point matches, then we do indeed have a pure sample. That is one way that we could test for purity, and that is probably the example that I would use here. However, if you gave an alternative response, saying that we could test the sample using thin layer chromatography, and if only one spot was present, the sample is pure, that would also get you the marks as well. So we've got more than one option there. Now, because this is a 6-mark question, we do need to make sure that we give a very well-developed answer. We can't just give half of the method and a little bit on this and a little bit on that, or everything's in a big mishmash order. We need to make sure that the preparation, the recrystallization and the purity steps are all included. There are no errors and it is all in a logical order. So it's a tricky question, and I think all these experimental methods can really trip up students. They're not there in the standard bit of the textbook. You've got to go to a special part. It's just easy to miss it. So have this as your big warning. Don't underestimate all of the experimental techniques that you need to know. If you feel like you've glanced over them in your revision, now is your big warning just to go away and make sure you get working on those too. Because you'll find 1, 2, maybe even 3 of these come up across your A-level of 6-mark questions. And that's the thing, they are often 6-mark questions. So make sure you get learning them, because that could really, really impact your grade if you skip over them. But good work. I hope that that is feeling good and you're feeling confident. DMAC, C4H9NO, is an important solvent in chemistry due to its polarity and relatively high boiling point, which makes it better suited than many organic solvents. It is mostly used in the pharmaceutical, agriculture and textile industries. The structure of DMAC is shown below. Here we're asked to name the functional group in DMAC. So let's have a look at this. I can see this functional group here. I can see a carbon with a double bond O attached to an N. And I know that that is the amide functional group. And so that's the answer here. So now in part B, we're asked to state the IUPAC name of DMAC. So to do this, let's first just draw this out again, just so that I can scribble all over it and illustrate this for you. We have an amide here, and see that that nitrogen is actually attached to 3 carbons, isn't it? It's got 2 methyl groups coming off of it. Now, because it's attached to 3 carbons, what we have here is a tertiary amide. And when naming tertiary amides, we have a very particular method. So we are going to call this NN-dimethyl to represent those 2 pink methyl groups. And it's an amide, isn't it? If you look here to how many carbons are attached to this double bond O, I can see 2 carbons. So I know that that's going to be ethanamide. So I've got NN-dimethyl to show that I've got this tertiary amide with 2 methyl groups attached to it. And then on the other side of it, that carbon double bond O has a chain of 2 carbons, and so that's ethanamide. So NN-dimethyl ethanamide. That is the name of DMAT. Now this molecule here, this C22H48ClN, is used as a disinfectant for linen and a sterilizer for surgical instruments due to its antibacterial and antifungal properties. So a molecule of this substance is shown below. A chemist proposed the following synthesis pathway to DDAC from DMAC and DEC-1-ene. Substance W is the minor product from the reaction of DEC-1-ene with HCl. Draw the reaction mechanism for the synthesis of substance W from DEC-1-ene and HCl. So let's draw out DEC-1-ene here first. So it's quite a big molecule, so it takes a bit of a while. So now we know that we're reacting it with HCl. So let's draw HCl on here too. Now the next step, it's really important that we draw on our dipole within the HCl. H is delta positive and Cl is delta negative. Now for the curly arrows. So we're going to have a pair of electrons move from the CC double bond to the delta positive hydrogen, and then away from the HCl bond towards the delta negative chlorine. Now in doing this, we break that double bond, forming a carbocation, and we also form a bond with the hydrogen. And at the same time, we have broken the bond between the hydrogen and the chlorine, leaving us with a chloride ion. Now, importantly here, we know W is the minor product, and that's what we're aiming to find. And the minor product forms from a primary carbocation, which is going to be less stable. So as a result, we're going to put our carbocation right on the end here, this primary carbocation, and that's going to ensure that we make the minor product of this reaction. So like I said, by breaking that bond between the hydrogen and the chlorine, we form a chloride ion which has a lone pair of electrons. Those electrons are going to move to the carbocation and it's going to form a bond there too. And that then leaves us with our final product of our minor product, W. So part 2, we're asked to explain why step 1 will produce a major and a minor product. So let me clear a little space here just so that we've got some space to write in our answer. So the key reason why we would ever get a major and a minor product is due to the fact, in this case, the decene is unsymmetrical. So whenever we have an unsymmetrical alkene, we will get minor and major products. And the reason for this is due to the differing stabilities of the carbocation. So for instance, the minor product, like we mentioned here, has a less stable carbocation. It's going to have a primary carbocation, whereas the major product will form from a more stable, perhaps secondary carbocation. And so that is what we need to know here. And this comes up all the time. I'd be very surprised if this didn't come up somewhere within your 3 papers. So make sure that you're really clear on minor and major products. Step 2 produced substances X and Y. Identify what type of reaction step 2 is and identify the reagents and conditions required. So what we need to recognise in this question to answer it is what functional group we have in the DMAT. I can see by looking at this that I have an amide bond. And I know I can break apart that amide bond in one of two ways. I can do acid hydrolysis or base hydrolysis. Now in this case, the fact that we make an amine tells me that I have base or alkaline hydrolysis. So when asked to identify what type of reaction step 2 is, the answer is alkaline or base hydrolysis. And the reagents and conditions that we need for this reaction to take place is simply going to be a hot aqueous alkali. We could give a specific example, such as hot aqueous sodium hydroxide. But make sure that you know that those are the conditions we need for alkaline hydrolysis to take place. Now we're asked to draw the displayed formula of substance Y. Now let's have a look at this breaking of this bond that we have here. We can see that half of it's going to break apart and become this substance X. The other half is going to break apart, and as it was base hydrolysis, we're going to add on an O- and an Na+. So what we've made here is a carboxylate salt. When the sodium hydroxide hydrolyzed the DMAT, what happened was the hydrogen from the sodium hydroxide went to the amine side, and the O- Na+ went over to our salt side. And so here what we end up getting is CH3, as you can see here, with a C double bond O connected to an O- Na+. And that there is our displayed formula of substance Y. So a student said that step 2 could be replicated by heating DMAC with dilute hydrochloric acid. Here we're asked to explain why the student is incorrect. So what would be happening in this case is if we use dilute hydrochloric acid, instead we actually have acid hydrolysis taking place. And acid hydrolysis makes slightly different products. We're still breaking apart that bond. However, you don't end up making an amine, you end up making an amine salt. And instead of making this carboxylate salt, you end up making a carboxylic acid. In this particular case, you'd end up making ethanoic acid. So as you can see here, these are the products that we would end up making if we actually did acid hydrolysis using hydrochloric acid. And you can see that they're clearly different products. So this question was really just testing you on your understanding of the differences between acid and base hydrolysis. So really do make sure that if you're not quite sure on the difference between those types of hydrolysis, that you just go away, make a few notes on it, and make it your priority to get them solidly in your head for the next question that comes up on it. Now we're asked to write balanced equations for step 3 and 4. So let's think about step 3 here. We've got substance W, which we worked out earlier was C10H21Cl. And we're told that that is going to undergo a chemical reaction with substance X. Now the formula for this is CH3 2NH. So what we need to recognise here is that substance W is a haloalkane and substance X is an amine. We have learnt that amines react with haloalkanes and they form an ammonium salt when they do. Now this is the reaction that we're going to use here to get our balanced equation for step 3. So in this particular case, for this particular reaction, step 3 is going to be C10H21Cl plus that CH3 2NH of substance X. And that's going to react together to make our final product here, which is going to be CH3 C10H21 NH plus Cl minus. And that is the ammonium salt that's going to form in this reaction. Now let's have a look at step 4. So step 4 is going to take that ammonium salt that we've just made and react it with sodium hydroxide. So using what we've just said we made, the CH3 C10H21 NH plus Cl minus, and reacting it with sodium hydroxide, we need to make sure that this makes an amine, sodium chloride, and water. Now this is again a standard reaction that we are expected to know. If you're not familiar with this, then now is the time to make some notes on what I'm saying. So in this particular case then, we need to know what particular amine would get made in this case. So we're going to have CH3, 2, C10H21, and then N. And we're also going to have H2O, and we're going to have NaCl made as well. So there we have it. That is our reaction. Do make sure that if you don't know those, you don't leave this till another day. You stop the video right now and just make some notes on this so that you don't forget it again. So next up now, the last part of this question, for us to name the mechanism observed in the formation of both substance Z and DDAC. So this mechanism is taking place when our halogenoalkane reacts with our amine. Now the nitrogen atom of that amine is going to act as a nucleophile, and therefore we have a nucleophilic substitution reaction in this case here. And so that is our mechanism. This question is about hydrocarbons. Alkanes are saturated hydrocarbons. Explain what's meant by the term saturated hydrocarbon. So in this definition really there's two parts that we need to define, hydrocarbon and saturated. So let's start with hydrocarbon. We should know that a hydrocarbon is a compound or a molecule that contains only carbon and hydrogen. And that word only is critical to getting your mark. So now that we've got that down, let's think about the meaning of saturated. So we need to know that a saturated molecule is one that contains all single carbon-carbon bonds. There are no double bonds anywhere within that. So there we have it. If you don't know those definitions, make sure you get learning them. So now we're asked to state the general formula for the alkane homologous series. So in this case, again, this is just something that we should know, and this is something you would have known since GCSE, so hopefully you know this one. And the answer is CnH2n plus 2. However, of course, if you don't know this, then just pause the video now, get your flashcards out, and get writing it down so that in the exam you don't miss out on easy marks. Alkanes are used as fuels. One example is hexadecane, which is C16H34, which is found in diesel and is a liquid at room temperature and pressure. Here we're asked to construct a balanced equation for the complete combustion of hexadecane, and make sure that we include state symbols. Well, they tell us the formula is C16H34. Combustion involves adding it with O2, and as it's complete combustion, we know that we only form carbon dioxide and water. So, looking at this, I can see I need 16 carbons on the product side, so 16 CO2 does that, and I need 34 hydrogens on my products, which 17 waters will do that. Now let's think of how many oxygens we have. I can see that from the carbon dioxide, the 16 carbon dioxide, I can see I have 2 times 16 or 32 oxygens. Within the 17 waters, I have 17 oxygens. So I need to tally up how many in total I have on this balanced product side. 32 plus 17 gives us 49 oxygens. And so if we look on the reactant side, we see we have O2. So we need half of 49 numbers of O2. We need 24.5 O2s. So that's all balanced. However, we need to include state symbols. Don't forget that. Now the question tells us that hexadecane is a liquid at room temperature. So that is a liquid. The others we're expected to know. Oxygen is a gas, carbon dioxide is a gas, and water is a liquid. So hopefully you had no problem with that question, but by all means, if you had any troubles, just make some notes on it. So now we're asked to calculate the volume of oxygen that would be required to fully combust 1 litre of hexadecane at room temperature and pressure. And we're told to give our answer to the nearest whole number. We're told the density of hexadecane is 0.77 grams per centimetre cubed. Well, an important statement within this is the fact this is at room temperature and pressure, because there's a fact that we know about that condition. We know that when we have 1 mole of gas at room temperature and pressure, it occupies a volume of 24,000 centimetres cubed, or we could write that as 24 decimetre cubed. So that's going to come in handy here. However, before we can work out the volume of oxygen, we're going to need to know the moles of oxygen. Now at the minute we know that we have 1 litre of hexadecane. We need to know that 1 litre corresponds to 100 centimetre cubed. Now as we know the density of hexadecane is 0.77 grams per centimetre cubed, we can work out the mass of hexadecane simply by multiplying its density by its volume. Now that gives me a mass of 770 grams of hexadecane. So the thing that we're going to eventually need to know is the moles of hexadecane, because then we can use our ratio between the hexadecane and the oxygen to work out the moles of oxygen. However, first things first, to be able to get the moles of hexadecane, we know its mass, but we need to know its MR. So the formula is C16H34. So the MR will be 16 times 12 for the carbons, plus 34 times 1 for those hydrogens. Now, popping that into the calculator, I end up finding that my MR is equal to 226. So now I know that moles are going to be the mass over the MR. So to get the moles of hexadecane, I'm going to do 770 divided by 226. And that gives me 3.407 moles. So that is the moles of hexadecane. We're being asked about oxygen here though, so if we look to our balanced equation, I can see that we have a 1 to a 24.5 molar ratio of hexadecane to oxygen. So I know that if I need to get the moles of oxygen here, all I need to do is multiply those moles by 24.5. So the moles of oxygen is 3.407 times by 24.5. And that ends up giving me 83.4715 moles. So we're nearly there now, because now that we know the moles of oxygen, we can work out the volume of oxygen. So we said that every mole of a gas at room temperature and pressure occupies 24 decimetre cubed. We're going to go with the decimetre cubed over centimetre cubed because that's what the units are on the answer line. So here, to get the volume of oxygen, we take the 83.4715 moles and we times it by 24. That gives me 2003 decimetre cubed. And as the question wanted us to give our answer to the nearest whole number, that is our answer. Analysis was conducted on a hydrocarbon Z. The elemental analysis found it to have a composition of 84% carbon and 16% hydrogen. Mass spectroscopy showed the molecular ion peak was found at 100. The carbon-13 and the proton NMR spectrum are shown below. So here's the carbon-13 NMR, and here is our proton NMR. Using the information, we're asked to identify the saturated hydrocarbon Z, and we should include a skeletal diagram of compound Z and give the IUPAC name. So there's a lot of information here, and because this is a 6 marker, we need to make sure that we analyse all of this information and give all the information required to get our full marks. Now let's get started with the information that was given regarding the elemental analysis and the carbon-13 spectrum. So we were told that the elemental analysis found this hydrocarbon Z to have the composition of 84% carbon and 16% hydrogen. Now the importance of this information is we're now able to work out the empirical formula of this compound. So I'm going to write the carbon and the hydrogen up here, and I'm going to write down 3 rows. I'm going to have the percentage by mass, the MR and the moles, and I'm going to fill in the relevant information. So I know I've got 84% carbon and 16% hydrogen. I know that the MR of carbon is 12 and the MR of hydrogen is 1. I can see that simply by doing 84 divided by 12, which is essentially mass over MR, I get moles. And although it's not literally how many moles, because of course this is the percentage composition, it's not the actual mass, it's going to be proportionally correct. So then with the hydrogen, we've got 16 over 1, which gives us 16. So normally when working out an empirical formula, you don't get such nice numbers. Normally you have to do an extra step to get the simplest whole number ratio. However, 7 and 16 is already our simplest whole number ratio. And so as a result, we can just crack straight on and say that our empirical formula is going to be equal to C7H16. And that there is our empirical formula of this hydrocarbon Z. So now if we look at the other information given, that the molecular ion peak was found at 100, we can then try and work out what the molecular formula is. Now the way to do this is to first work out the MR of your empirical formula. So in this case, this will be 7 times 12 for the carbon, plus 16 times 1 for the hydrogen. And if I calculate this, I find that I get 100. So what we want to do is to compare the MR of our empirical formula with that of our molecular ion peak. And in this case, I can see that they are the same. Now, because they're the same, I know that actually the molecular formula is also C7H16. So now I know how many carbons and how many hydrogens I have. Now let's move on to our carbon NMR spectrum. So in my carbon NMR spectrum, I can see that I have 3 peaks. Now that tells me that I have 3 different carbon environments. And that's going to be really important when it comes to drawing the structure of this substance. If we have a look at the chemical shift values, I can see that all of the chemical shifts exist from 20 up to 50. And so from that I can say that we've only got single carbon-carbon bonds within this hydrocarbon. There's no peaks corresponding to an aromatic or a C-double-C bond, so we know we're only expecting to have single C-C bonds. So we've got a saturated hydrocarbon here. So now let's take a look at the proton NMR. Now in this case, I can see that I have 3 peaks again. This means that I have 3 proton environments, or 3 hydrogen environments, we might prefer to think of it as. Now, whenever I have these proton NMR spectra, I like to draw a little table because there's just so much information held within them. So when I write out these tables, I like to have a column for the chemical shift value, column for the number of protons in each environment, column for the splitting pattern as well, and then finally a column for the identity, which is going to be corresponding to our chemical shift value. So here, as you can see, we have 3 different peaks. So let's get started first with the peak that has a chemical shift value in the range of 0.7 to 0.8. Now here I can see, due to the 12 in brackets above it, that it's going to have 12 protons within that environment. I can see that its peak has 2 parts to it, so that means it's a doublet. And I'm going to say that a doublet is going to be adjacent to a carbon with only 1 hydrogen. And that's using our n+1 rule. And finally, the identity, if I look up that chemical shift value, I can see it is going to correspond to an HCr. So let's now move on to our next peak. Let's do the one with a chemical shift in the range of 0.9 to 1.1. This has a little 2 in brackets above it, which tells me that there are 2 protons in that environment. I can see it's split into 3, so it's a triplet. Now this means it's going to be adjacent to a carbon that has 2 hydrogens attached. And then finally the identity, again, it's going to be the same as the previous one, HCr. Now this final peak here is in the region of 1.4 to 1.8. It's got a 2 above it again, so I know that there are 2 protons in that specific environment. And in this case, I can see that the splitting pattern is what we call a multuplet. If we ever have more than 4 peaks, it's absolutely fine just to refer to it as a multuplet. Now, a multuplet is going to be adjacent to a carbon that has many hydrogens attached in that case. So it's going to have a lot more going on. We know that there's a really big group here with lots of hydrogens. Now again, for that identity, it's the same as the others. It is going to be an HCR. So there we have it. We have analysed everything that we can now. Now we need to try and bring together all of the information from both of these pages and see what we can get. So we don't need this spectrum anymore because we've got all of the information out of it. So let's tidy that up and get rid of that. Now, let's have a think. We know that there are 3 proton or hydrogen environments. We also know that we have 3 carbon environments. We know that the molecular formula of this substance is C7H16. And we also know that we only have single carbon-carbon bonds. So, as we have 7 carbons, and yet we have only 3 hydrogen and carbon environments, this tells me that there must be some branching and there must be some level of symmetry in our molecule. So sometimes it's best just to have a go at drawing a potential structure and see where you get on with it. So here I'm going to draw these 3 carbons here. In the middle, I'm going to treat this carbon here as almost our middle of our symmetry. And I've got 2 hydrogens attached to that one. And then each carbon either side of that central carbon, I'm going to add on 2 CH3 groups and a hydrogen. And I'm going to make it symmetrical so that, as you can see, both sides have the same. So here I can see that I have 1 hydrogen environment belonging to that central carbon. Both of those 2 hydrogens are in the same environment. So if I draw my little mirror line, hopefully you'll see why we don't need to count twice. So if I just look to one side here, those hydrogens that I've highlighted pink both represent the same environment due to that symmetry. So that's our second hydrogen environment. Next, we've got the hydrogens belonging to all of these CH3s. And again, due to symmetry, actually, they are all in the same environment. And notice, because there's 4 of these 3 hydrogens, that is the same as 12 protons. We've got that in our table, haven't we? We said that for that chemical shift value of 0.7 to 0.8, we have 12 protons. And we also know that should be next door to a carbon with 1 hydrogen, which it is. So that fits perfectly. So far, so good. Now let's look at this other region, the pink hydrogens. Here I can see that there are 2 of these hydrogens, so that fits. And they're next to carbons that have many hydrogens attached. So that is indeed correct. So yes, that environment is fitting as well. Finally, let's have a look at our green hydrogens. So we can see that there's 2 hydrogens in that environment, yes. And we can see that they are next door to a carbon that does have 2 hydrogens attached. There was this one and this one. So again, this fits perfectly. Great. We have got everything fitting. We have 3 proton environments. Let's double check the carbon environments. And then if that works, then we should be pretty much good to go. So I can see that these carbons are all in the same environment, again due to that symmetry. These 2 carbons are also in the same environment, again due to that symmetry. And finally, this is our 3rd carbon environment. So there we have it. We have got everything working there. So now we can finish off this question by writing it as a skeletal formula as requested in the question, and also by naming it. So let us first have a go at doing its skeletal formula. I can see that I have got a long carbon chain here that has 5 carbons within it. So this is my longest carbon chain here. And I can see I've got 2 methyl branches off of that. So for my skeletal formula, I'm going to go 1, 2, 3, 4, 5 carbons. And on my second, And my 4th carbon, I have methyl groups. So using that fact that we have a 5-carbon chain alkane, I know its name is going to end in pentane. I can see it has 2 methyl groups, so it's a dimethyl, and they lie on the 2nd and the 4th carbon. So naming this, I get 2,4-dimethyl pentane. And that there is our answer.
Ouch! This is why in some videos I'll explain scratches.